Here for today is Dr. Abu Siddique. Okay. And the title of his talk is Recommender Systems, Bridging Gaps in Data, User Behavior, and the Conversation. Okay. Dr. Siddique will present their three words. The purpose is to address mobile app recommendation, okay? A uniquely challenging frontier. Okay? He will be presenting a very interesting topic, and so let's give him a warm welcome. It's yours.
Thank you. Okay. All right, I guess let's start with the hope that more people will join us soon. Okay, so I will talk about recommender systems. Essentially, I will present three of our works we have done over the past few years about data set, about some issues in user modeling we improved, and then some further improvements in conversational recommender systems. Okay, so let's jump right in. Recommender systems. So essentially, recommender systems track our activities, model our behaviors, and make recommendations for us. Okay, so we are using recommendation systems either knowingly or unknowingly, most probably on daily basis. So essentially, recommender systems decide whom we will befriend, what movies we will watch, what products we will buy, which news articles we will read, which music we will listen to, which restaurants we will go, which reels we will watch on TikTok, and who has watched Hang the DJ Black Mirror episode? Okay, okay, a couple of people. All right, so those of you who have not, please do so. So essentially, in this special episode, they had a special dating application. They named it Coach, and that application will match people for a certain amount of time. And those of you who have watched, they know what happened in the end. They decided to go out of the matrix. All right. All right. So the point I'm trying to make here is that recommender systems are prevalent in many domains. And because the topic of today is not about free will, okay? So Wikipedia definition of recommender systems is a subclass of information filtering system that provides suggestions for items that are most pertinent to a particular user, okay? In simpler words, recommender systems try to reduce information overload by matching relevant items to relevant people. Okay. Recommender systems have great business value. For example, recommender systems are responsible for 75% of movies watched on Netflix, 35% of sales on Amazon, and 38% more click-through on YouTube ads. So what has happened is recommender systems essentially collect some information about us, and then they use that information to make recommendations. Okay, so what could be sources of information they collect? For example, whenever we rate something, rating could be 5-star based or binary rating, like-dislike based rating. Sometimes we also leave like textual reviews, or even pictures are there these days. It could be implicit, like just page visits, or we created a profile and left some information about ourselves. So all these are really good sources of information for recommender systems to model our behavior and start making predictions. Okay? So at its core, every recommender system looks like something this. So essentially we have, I mean this is very small, but it could be all the users here and all the products over there. And whenever we interact with a product, it could be like or dislike, whatever signal. So they create like this huge matrix. Okay? And from here, you could imagine that a lot of the cells will be empty because many people don't interact with many items, right? So, for example, this user just interacted with 3 items, and that's it, right? So, I mean, we cannot possibly watch all the movies on Netflix, right? So, so the goal of recommender system is essentially how to fill these empty cells, right? So this is the question essentially every recommender system tries to answer, okay? And this is an extensively studied research area, huge number of papers, how to essentially fill this number, right? So, and there are broad categories starting from collaborative filtering systems to content-based, then hybrid systems. Then we have seen knowledge-aware, context-aware, graph-based systems, session-based recommendations, sequential recommender systems, conversational recommendations, and more lately we are seeing generative recommendations as well. Okay. So out of all these, my favorite one is sequential recommendations. Okay. And one of the reason for my liking is that these sequential recommender systems try to learn our behavior with respect to time. Okay. So essentially what these systems do is they consider our temporal order of actions. And the hypothesis is that sequence of events matter, user interest evolve over time. So just compare these. So this is traditional recommendations where we don't know whether this user liked this movie first or this or this. But if we can model this in a sequence, we might have more information how user interests are evolving. Does that make sense? All right. All right, so moving forward, the task for the sequential recommender system essentially becomes simpler, okay? And the task becomes something like this. Given a user's historical interaction organized in a chronological order, the goal is to predict next item. Okay, pretty simple yet very difficult goal. Okay, so this was a quick, pretty high-level overview of recommender systems. In the remainder of my talk, I will talk about 3 of our works we have done recently. The first one is Mobile Rec. This is a large-scale mobile app recommendation data set. And the next work, this work appeared at SIG-IR 2023. Then the second work is Interpause. Essentially, this is, we will talk more about that. Essentially, this work considers unique rhythm of user interactions and tries to make better recommendations than state-of-the-art systems. This work appeared ICSC 2025, sorry. One of my students just presented yesterday. And the last work is still in progress, but available at arXiv. It's a framework that combines traditional click-based recommendations with conversational recommendations. Okay, let's move to the first one. So the first thing is gap in data, and the spoiler alert for this is this mobile rec data that we proposed a while ago. So as I mentioned, recommendation system is an extensively studied area, and in machine learning, those of you who do machine learning, and these days pretty much everybody does machine learning, know that data is important. If there is no data set, we cannot move forward. So in recommender systems, the data sets are pretty much available in any area. For example, Amazon, Movie Lens for movies, Retail Rocket, Goodreads, Pinterest, all these data sets, these are like large scale data sets for almost every domain are there. And at the time when we started exploring this were there. However, we did not find any data set for mobile app recommendations. And since there was no data set, the research was also non-existent in mobile app recommendation. Okay, and it's not that mobile is like a small thing. It's like a huge market with over 5 billion users, over 3.2 million apps, but still no data sets were there to make mobile app recommendations, and and subsequently there were no recommender systems in the mobile app area. Okay, so this is the state of things when we started exploring. These were like the biggest data sets out there. If we look at some numbers look really good. For example, this data set had 9.3 million user reviews. So it's big data. And number of apps about which these reviews were is also decent. It's a big number here and decent number here. Although these are small number, but these are reasonable numbers. Similarly, the categories these data sets cover were also good, especially this one. And a lot of the time, review text was also available. For example, in all of these data sets, the review text was there. Review rating was also there. So this is the first thing that was missing. And a lot of these data sets, except one, did not provide app metadata. App metadata is essentially what is the name of the app, its rating, its category, information like that was not available. But this is not a difficult thing, right? So even in the biggest data set, this number is about 1,600. We could just go and write a simple crawler, and that will extract this information, and we will be done, right? So first challenge was that all these reviews, in 3 of these data sets, this timestamp was missing. So if there is no timestamp, we could still build a recommender system, but we could not build sequential recommender system. Does that make sense? Because we need to organize the items in sequential order. So if we don't have this information, we could build some other recommender system. So this was, and these 2 data sets actually contained timestamp as well. Okay, so but this is the main challenge. In all these data sets, at the time, no data set contained more than 1 user interaction. So there was only 1 user review per user. So if we have just 1 user activity, you can imagine there is nothing to learn about that user. And even if we could, how we will evaluate? So this was the challenge at the time in mobile app recommendation. So we thought, let's go ahead and collect and build a big data set. Okay. So yeah. So yes. So this is where I talk about first challenge about data crawling. So if it was a static website like we have KCS, it would have been crawling. This website like this is like straightforward, right? We don't need to do anything. We just run this command, get the DOM, parse it, and we are done, right? Those of you who are familiar with crawling should know, right? Similarly, with dynamic websites, crawling is still fine. We can work through. Whenever we click somewhere, for example, this next, the URL changes, and we can figure out these patterns, and we could write a crawler that will keep going to, that will keep changing this URL to page equals 2, page equals 3, page equals 4, and then get the DOM and parse it. Okay. So the problem comes when we have interactive web pages. So interactive web pages are those when we click at some element and the URL of the page does not change. So for example, this is old Google Play at the time when we crawled the data. So if we click on this most relevant, the URL will not change. Okay. Another challenge is that this some reviews are not fully available, so we actually need to click on this item to get the full review. And when we do all these interactions, URL does not change. So what is the meaning of that is that if we need to extract all the contents that are part of the DOM, first we need to perform some action, and then those parts will become of the HTML DOM, and then we can extract those. And this was true everywhere, because Google Play will only give you 40 user reviews, and as you scroll to the bottom, then the 40 more will load. So you need to keep scrolling to get more URLs, more user reviews without changing the URL. So essentially, to extract the content, you need to interact with the page. Otherwise, you will not have access to all the content. Okay. So those of you who are familiar with web development, you guys know how to build such websites. These are AJAX-based websites. So they asynchronously send requests to the server, get the content, and update the URL without reloading the full page. So essentially, the URL remains the same, and we get the new content. So essentially, this technology is developers' dream, but nightmare for people like me who want to crawl data. Okay. So here comes Selenium driver. So what is this? This is a package we could use to programmatically interact with web pages. Okay. So, and it is available in many programming languages, works with almost all the famous web browsers. Okay. So what we could do is we could write a code like this that will load a URL, and I could parse the DOM and actually write this code. Find this element, click there, and that will actually perform this action without me clicking there or any human being clicking there. Okay, so this code could actually programmatically interact with a web page, fill my DOM with the content, and then I can extract the content. So kind of problem solved, right? So essentially, this has a bunch of methods where we could locate certain elements from the HTML DOM. We could extract content, perform actions, all sort of things. Okay. So long story short, we use Google Play, and as I mentioned, those reviews will not automatically load, because they just show part of the reviews. Okay. So we use Selenium, and we were able to collect some data. We collected package names that will uniquely identify each name, collected metadata, we downloaded a lot of reviews. Okay. So essentially, this data set captured user activities on Google Play, and after some filtering and everything, we were able to keep 19.3 million user interactions for over 10,000 applications from 48 categories. And in our data set, each user had at least 5 interactions. So meaning we will have at least 3 user interactions for training, fourth could be used for validation, and fifth could be used for testing. Okay. And for privacy reasons, we also anonymized these user names. So we just put some, we generated these 16 character UIDs for each user, and then we assigned those. Okay. And this is like a quick comparison with existing data sets at the time. This is a table you would like to have in your papers, where if there are numbers, your numbers should be bigger than others, and if there are crosses, you want to see all things ticked. So we did that. Okay, and so yeah, in short, this is like 19.3 million user interactions over 10,000 apps in 48 categories. We kind of tried to cover everything. So this is the comparison with the existing mobile app data sets. But as I mentioned, recommendation is extensively studied thing, right? So we also compare it with other domains data set that were very popular at the time. And this is mobile rack, and it's comparable to existing data sets. You might be wanting, these numbers are way bigger than everything else, including ours. And the reason is this Amazon reviews, this is actually a union of many data sets. So they have beauty, they have electronics, grocery, garden. So these numbers represent, if we combine all those into one giant data set, that's why we have very, very big numbers here. But if we split those, all these data sets were very, very comparable to one another. Okay? And these are a few of the features we had collected during our crawling and everything. We had this UID, package name, app name, review text, rating, votes, and also this time step to organize the users. These were a few of the top categories in our data set. And we also had nice plots in the paper. So essentially, these plots are showing how people move from one category to another. Okay. So let us say this one. This one is telling how many people that use that install simulation-based app move to other category after that. Okay. So if we have data set like this, where we have user interactions organized in a chronological order, we could actually go ahead and build a recommender system that could start making recommendations for app installations, right? So what we did was we built some baselines using this data set. For example, we built pop-up is a very straightforward baseline that doesn't do anything smart, but this is a good to have baseline. What this does is it just recommends you popular items. Okay, and a lot of time that works great actually, right? You can think of this as in classifications we have this majority class classifier that always recommends you whatever the majority class is, right? So this is equivalent to that. Then we built some other baselines in sequential recommender systems. In transformer-based architectures, we use LightSAN and session-based recommendation and graph neural network-based recommendation. And for evaluations, we used hit at k and NDCG at k. So essentially, hit at k tells us that the likelihood of finding the ground truth in the top k list, and NDCG essentially captures the comparison with the ideal ranking. Okay, and yeah, this is just a slightly difficult way of saying what I just said. Okay, and yes, for hit at k, for hit at 1, we saw that SASREC was the best model out of these. At hit at k, we found out LightSANS was the best, and similarly, most of the time SASREC was good, but at other places LightSAN was better. Any questions so far, or everybody is with me? Everybody is with me? Yes.
when you have, sets or reviews, of course, you don't create those reviews yourself.
Yes.
But how do you know those reviews are real reviews, not, people build just to make their, views more popular? So how do you make sure those are real reviews?
Yes, we don't do anything for that with the assumption that Google Play has such mechanisms to find fraudulent apps and block those. So at the time when we did crawling, we were hoping that everything is already blocked. And since this process went on for many days, maybe months, so some apps during our process were also blocked, so we removed all those.
So you simply assume
Those are real reviews, genuine
all
reviews.
right.
Because these platforms have such mechanisms in place. We did not do anything. All right. So while we were building these baselines, we figured some gap in the user modeling as well. How these existing recommender systems model our behavior. Okay. So in order to understand the issue, let us go ahead and see how we model language. And this is the other reason why I like sequential recommender systems, is because I work in NLP, and modeling of natural language is pretty similar to modeling items, user behavior. Okay? So let us quickly see how we do user modeling with traditional RNNs. So the goal in language modeling is predict next word, right? So let us say if I input start of sequence, the goal will be to output robot. Okay, and since this is an RNN, it will output a hidden state, and I can use this hidden state to run it through a classification head to make a prediction. And you can think of this as the embedding layer. Okay, so and then at next time step, I input robot, and the goal is to output must. At the next time step, I input must, and the goal is to predict obey. Okay, so this is how we do language modeling, right? So this straightforwardly just follows in the recommendations. So for example, if this is my these are chronologically organized user interactions, I could just, instead of inputting a word, I could input my first item in the sequence. Okay, and the goal here will be to predict Instagram. The next time I could input, at next time step, I could input Instagram, and the goal will be to output Snapchat. The next time step, Snapchat, and the goal will be to output TikTok. Okay, everybody is with me? Pretty straightforward, right? But more recently, you might have noticed that nobody uses RNNs, LSTMs, GRUs. Nobody cares about those. The reason is everybody uses GPT these days, right? Language models. So the phenomenon in GPT is also pretty similar to what we did in RNNs, right? Whenever we input a word, the goal is to predict next word. The objective is still the same. Okay. The major difference is in the processing. So in RNNs, we input things sequentially, output thing, then go to next time. So this is like the sequence. But with GPT or all these language models, modern language models that follow transformers architecture, they process things in parallel. They could process all the tokens at once. Okay, so the question is, if we can process all the tokens at once, how we will know what was said before and what is being said after? And if we want to generalize it to recommender systems, how we will know that what is the item that user liked at time step 1, at time step 2, and so on, right? So if you are familiar with transformer architecture, you might already know that we have token embeddings, and the thing that takes care of the order is position embedding, right? So what do we have is, we build an similar to embedding matrix, we build this positional encoding matrix that this is my context size, let us say 1024 depending on the model I'm using, and then this is the size of the embedding I have decided. So whenever I input something, let us say I want to input start of sequence, you can think of two very simple lookups. Lookup for my token embedding and lookup the order, the position of this word. Now I can add these two and start passing it to the model. Now when the model will be processing everything in parallel, this position embedding will take care of the position of this word. So essentially, the model will be able to know the position and will know what was said before and what is being said now or in the future. Good? So we can just assume the same formulation in sequential recommendation systems as well. What do we need to change? We need to get rid of this token embedding and bring in item encoding instead. Right? So instead of having this word embedding, we could have this item embedding that will learn the embedding of my items. Let's say in this case, embeddings of these apps. Okay? And then I could still keep this position embedding that will capture the position, the position of this interaction. Okay? I could similarly perform lookups, add these, and start inputting to the model. Sounds good? Right? Do you see any problem here or no? Not yet. In a minute you should see. So one major difference with language modeling and this recommendation system is that in language we have words here and all the words are just one word away from another word. And in this case, we don't know. So I might have this interaction on this date, and after 12 days I had another interaction. And the extreme case here, you see, there was 171 days gap between two interactions. So if it was language, that was perfectly fine because I will not stop here and wait 171 days to speak the next word. Okay? If that was the case, then we might not be able to model the language like this as well, right? But in this sequential recommendation, this is a big problem. And before our work, everybody will just discard these, will not care the gap between interactions, and will just say, oh, this is my interaction 1, interaction 2, interaction 3, interaction 4, 5, and we'll just model it as a language. Okay? So our idea here is that we should consider user rhythm. Rhythm meaning how temporally different, how temporally apart these two items are. Even though these are two consecutive interactions of user, but what's the gap between these two? Okay, how far these two items are from one another. So what we did was, we thought, this is essentially one of the idea. People could do maybe much better than this, right? So we just computed what's the difference in number of days. Okay, so we just subtracted these T2 from T1, and we figured, oh, this is just 12 days gap. Same here, all the way. So in terms of on top of position, we could also use this to better model the user behavior. Okay, so this is like the key idea in this work. Okay, and I will go over quickly a few model variations we developed. So this is a traditional recommendation system, traditional sequential recommendation. This is my embedding layer that will learn the item embeddings. This is a positional embedding, and we will pass these to the recommender system. Okay, so what we did, the first idea was, now we are also learning this rhythm thing. Okay, that captures how temporally apart are two given interactions. Okay, so this embedding. So we just add these two and pass it to the model. This is like pretty straightforward way of doing things, right? So when we were doing it is too simple, will not give us results or something like that, right? And so we thought, okay, maybe we should come up with some better mechanisms. So we had another idea that where we concatenate these two embeddings and pass this through MLP and then pass it to the model, okay, with the hope that this MLP will learn some interactions between these two, okay. And the third idea was like pretty sophisticated. We thought this should give us the best result, but most of the time simpler ideas actually gave us better results, right? So here we had this gating mechanism. So this gating will decide, oh, how much importance should I give to position embedding and how much importance I should give to the user rhythm. And then we passed this information to the recommender systems. And in terms of implementing, here we used two different architectures. We used SASREC and we used LightSAN. I will be presenting some brief results here. And yes, so this is action dataset. Action is essentially a subset of our full dataset that just talked about action apps. Action is a category on Google Play, Android, right? So yeah, most of the time we saw that this simple strategy that will just add up two embeddings. That's it. That worked well. And by the way, this is hit metric, okay? And then yes, once again, for action dataset, on all three, hit at 10, 15, 20, this was the best one. So these are results on the full data set, okay. Here we also see the second one where we are doing this concatenation and passing through MLP gave us better results, and some more results. I mean, the paper we had like big tables to impress the reviewers, okay. If you are ML person, you know why we would do things like this, okay. So this was the second work, and after we were done with this work, since I work with natural language a lot and dialogue systems a lot, we thought maybe we should do something better than these traditional recommendation systems, okay. So this is an ongoing work, still archive version is there, okay. So in traditional recommendation system, so far I have talked about, essentially they follow user item interactions and they try to learn implicit preferences of users. So essentially we don't have a lot of information, we just have these clicks or sometimes user reviews, and the system is trying to learn what are the implicit things there in this app or in this app or in this app that the user likes, or how the user interests are evolving. User does not explicitly say much, even if there are reviews available, but those reviews don't reveal a lot of information about the user's preferences or likes or dislikes, okay. So there is another category of recommender systems. Those are known as conversational recommender systems. So what conversational recommender systems do is they can chat with the user and try to get information, like explicit information from the user. For example, what would you like to have, or it could be specific questions that try to extract user preferences explicitly, okay, not implicitly, okay. So if we summarize, there are two lines of work to essentially disjoint literature directions. The first is just click-based. These try to learn implicit preferences of user, and you can imagine this data is very easy to acquire. You could easily go and build a data set, and then you can actually build a recommender system as well, right? And yeah, one interesting thing about these is that since these capture implicit preferences, there might be some preferences that user, him or herself, is not aware of, might be hidden in these, and these recommender systems can actually capture those, okay. And in the other line of work, that is sequential recommender systems, they try to capture explicit preferences. They ask specific questions and use those answers to guide the recommendation. And intuitively, you might think that essentially these are taking care of immediate needs of the user, that user wants right now, right? And there is another opportunity. The opportunity here is that since this is an interaction and an active interaction in natural language between user and a system, there could be a follow-up questions as well. For example, system makes me a recommendation about something. I could ask, oh, does this thing have blah, 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 right? And then recommender system could tell me, oh, yeah, it has. And I might like the recommendation. Or the system could say me, oh, no, it does not have this. Then I could actually reject the recommendation and opt for another recommendation. Okay? So what's bad with each of these? Essentially, whatever is good here is bad here, and whatever is good here is bad here, right? So essentially, explicit preferences are mentioned here. There is no mechanism of explicit preferences other than just liking it or actually buying it, right? Similarly, this is pretty easy to acquire, right? We could write a crawler, crawl Amazon or Google Play like we did, and get like a lot of data. But getting this kind of data is pretty expensive, right? We need to get two users to talk with one another to get this kind of data. And since this will be like a simulated data, it might not represent like realistic conversations as well. Okay, so what we decided was that how about we combine these style of recommendations with this recommendations, like getting best of both worlds. Okay, so what we did was we said, okay, now we already have user preferences, the previous user interactions. At a certain point in time, we could actually go ahead and conduct this kind of conversations. Okay, so these are previous interactions of user. Let's say interaction 1, interaction 2, interaction 3. At interaction 4, we could actually get conversation like this. Okay, where we ask explicit questions. Okay, and then make a recommendation. After recommendation, user could actually follow up, and based on the response, user might reject that recommendation, and then based on this feedback and previous conversation and this, the system might make a better recommendation. Okay, so like combining two different research lines. So the problem here is that, as I mentioned previously, this data collection will be very expensive, and traditionally people use this Wizard of Oz style data collection where one person acts like a user and the other person acts like a wizard or a system that knows everything, can chat and then make recommendations. Okay, but as you can imagine, this will be very, very expensive. Okay, so what we did, we thought maybe we could generate these kind of conversations automatically using LLMs. Okay, so I will quickly go over how we did. First we had designed a theoretical framework to do that, but here I will just go over like the actual working of the framework. Okay, so as a first step, we mined all the reviews and extracted key concepts from there. Okay, and if we have associated aspects with each user review, we could actually go ahead and build a user profile. Okay, so user profile will look something like this. For example, this person, these are scores out of 1. This person gives this much importance to app ratings. This person gives this much importance to this much importance to privacy, something like that. So if we have this information, we could also build global user preferences. If we combine all the user preferences, we could also build global user preferences. So essentially, this will tell us what are the aspects all the users care about and what are the things nobody cares about. Okay, so if we have this information, now what we could do is we could go ahead and sample one interaction, okay, from the data set. So just remember, this was just a click and some review was left there. So we are trying to use that interaction to simulate a conversation that follows the style I showed on the previous slide. Okay, so what we did was we gave this information, this user profile and this previous interactions and this sampled interaction to an LLM with a prompt that you have to simulate this user. Okay, and similarly, we gave another prompt to another user, to another LLM we called wizard LLM. So that has access to all the user's preferences, this interaction and this sample interaction. So the goal is that these two LLMs will talk to one another and simulate a natural language conversation, like I showed on the previous slide. And since we had this semantic level information, we could use that semantic level information to guide the conversation and know that this conversation is realistic as soon as these values stay close. Okay? So for example, we have this information about user profile, and then we sample a full conversation and see that this chat is not about these things that user care about, but it's about something else. We can just reject that conversation. Okay? So using this pretty simple framework, we were able to simulate conversations for all these data sets, for Amazon, mobile, all the categories of mobile rack, Goodreads, TripAdvisor, Yelp. Okay? And then once all the conversations were done, we removed inappropriate conversations using some classifiers that can detect obscene, the fluency things. Okay? So we removed, and there were not many, less than 10, I guess, in each data sets, such conversations were there. Okay, and then we also conducted human study on these, and most of the conversations were rated between 4 and 5 out of 5. Okay, and then we decided, okay, it's time to build a system on top of these. So what we did was we built two types of baselines. One type was this generative recommendations that will take dialogue context, just dialogue context, and make recommendations. And the other baseline was where we would prepend previous interactions, then conversation, and then the model will generate a recommendation for this user. And similarly, this is pretty similar, but in this case, the model will not generate a recommendation. We will give a set of candidates, and for candidates, the model will rank those. Okay? So essentially, if we just compute the probabilities for each items, using those probabilities, we could actually rank. Okay? And then see where the ground truth item was ranked. Okay? So our assumption was that these two baselines should perform better. Right? For example, when we have user previous interactions and this chat is there, this baseline should be better than these baselines when we just have conversation. We don't know user previous interactions. Right? So in many cases this was true, but this was not always true. In some data sets, we found that just the conversation is enough. We don't need previous interactions. And so to overcome this, we thought maybe the way we are passing previous interactions is not the good way. Because what we did, we just appended the plain items, and then this is the conversation, and that's what we did. We did not do anything intelligent, right? So we thought maybe there is a better way to do that. Okay, so we have built a cross encoder now. So essentially, what is cross encoder is we have one encoder that learns users' previous interactions from the click-based items. Okay, and we have another encoder that focuses on the current conversation, and then we cross encode these interactions and then make recommendations. For this model, so far we have not run this on all data sets, but we have run this on a couple of data sets, and we are having good results. Okay, so yeah, these were the papers that I mainly was talking about. The last one, even though it's not published yet, it's available there. Okay, and I would like to thank all my collaborators. These are from UCF, these are from LSU people, and these are my grad students who worked on these. I hope we have left some time for questions.
Yeah, that was an interesting thing to see. I don't understand a lot of machine learning stuff, but as far as I have seen and used it, combining the rhythm embedding was interesting. But one thing, I mean, I'm curious to know. So you said you weighed the importance of positional encoding, embedding, and the rhythm embedding, right?
There are three techniques. One was just simple addition.
Yeah.
The other one was concatenation and then running those through MLP.
Yeah.
The last one was gating mechanism where we actually combine these two, but this is like a weighted
Yeah, like a weight.
average.
Yeah, so I was only curious about one thing. I mean, has it ever happened? I mean, I know that might not be the case, but initially when you started the conversation, the first thing that came to my mind was that don't use a positional embedding, just use the rhythm embedding. Later on, you said that it is a rhythm embedding. So, has it ever happened that the importance given to the rhythm embedding is much more, and the importance given to the positional embedding is like negligible?
So we did not do this kind of investigations. We just checked the numbers.
Okay.
So numbers will tell us is this good or not, right?
Okay.
So to answer your question, I mean just use rhythm and not position. Actually, we cannot do that, and the reason is so the gap between two different users might not be the same. So we still keep the original order. So just imagine we have two interactions on the same day. So now the gap is 0.
Mm-hmm.
So now positional embedding will come into play, and that will tell us, okay, even though this is there, but they are still one item, one time step apart.
Got it.
Okay.
So there is the odds are low for producing a negligible like impact on rhythm, but the odds are pretty high that positional embedding would be given less important.
Yes.
Okay, got it. Yeah.
That
thank you.
was the main idea.
Yeah. Okay. Yeah. Thank you.
We have plenty of time for questions. Any questions other than, well, any questions? Yeah.
So I wanted to know if there are any, have you considered about the positive interaction and negative interactions, like positive reviews or negative reviews?
Yes. So essentially, in this, in the last one, we are just considering reviews that had rating 4 and 5. We did not use rating 1, 2, 3. We threw those away. So these are like positive interactions. These are not negative interactions. But in the original data set, mobile, that was like 19 million something. There, that was everything. It had negative, positive, and there has been debate in the community as well that is rating 1 better than no interaction at all? And many people believe that rating 1 is still better than no interaction at all. Okay.
Thank you.
Well, I actually have, questions for you, okay? Now, the recommender system, in my view, is just some kind of a ranking process, right? So obviously you have to use some statistic tools to do this thing, because you can never say this is absolutely correct, okay? So you can only say this is a 90% or 85%. So what kind of statistic technique are you usually used here?
Yes. So I mean, we know that this is true. For example, when we are training a model, we, let's say, take the future items for testing. So we know this is what user liked after this on this date. So we use that as a ground truth. So we don't need to rely on statistics or anything. So let us say if we had 10 item interactions for a user on certain dates, we will use first 8 for training. And then the 9th, the model will not use in the training. We will keep that for validation, and we know, oh no, the model is good enough. And Then the 10th one, we know this is the item that user interacted with, so that this item should be ranked number 1. So if that's the case, the model will get a score for hit at 1. Similarly, we could generate like a ranking of 25, and then we try to find the ground truth interaction. Where is this rank? Is it number 1, number 10, number 15, where? So if it's there, the model gets score according to that. If it's not there, the model gets 0. Right? So
Well,
yeah.
Google obviously, use some kind of, ranking technique. When we do a search, okay, usually the most popular answer would, pop
At the
up
top, yes.
first. So what kind of, technique were used, for instance, by Google?
So I mean, Google has published things in '97. Their page rank thing. I teach in one of my class. Those who have in my algorithms class, they know it, right? So essentially, they try to build this. How important is this page for this query? So they try to rank the importance, and how they measure the importance is how many pages refer to a given page, right? Of course, system can
So
do
that's
so they have like several.
more or less more statistic, approach.
Yes, so this is I'm talking about 96, 97, right? So now, of course, they don't tell, right, what they are doing right now. Most probably they are doing some deep learning model that will, given a query, will generate ranked. First, of course, they will filter the pages, and then after that they will rank. Okay, and yeah, you might have observed they also consider your location. So they bring in different aspects to re-rank things. For example, if I'm searching something from Lexington, the top results will be from Lexington, right? So because they use our location through Chrome, right?
So they have they have big data sets. So do you think that their recommendation would be more appropriate or more accurate?
Yes, and essentially the reason is, let me go back to categories, right? So these categories that I mentioned, these are not disjoint categories. People actually make use of many categories at once, and it's very early in the talk. Hopefully we will be there someday.
Any other questions? One thing I would like to remind you, yes.
We should have a prize for asking questions. Candy.
So in the
Prices of pizza.
in the click-based model you first made, what is the inference time, or what is the cost of inference for that?
Yeah, so in general, you can only focus on one thing when you are doing machine learning.
Mhm.
So if the goal is to improve the accuracy, you just forget about everything. Okay? And I mean, there are other lines of work that focus on this time reduction thing. So they do those kind of things. So in this work, our focus was just to improve the hit and NDGC metrics. Okay, I mean, this is how generally things are done. We just focus on one thing and that's it.
Got it.
Right? Yeah. So we did not actually capture those.
Anyone else? Oh.
So I had a question about the LLM wizard that you used. Which LLM that you used? Did you use any DeepSeek or Gemini Pro?
For conversational recommendations?
Yes, that you used
Yeah.
for training and 2 LLMs that you told us.
Yeah, so we did not do any training. These were chat GPT. We just prompted those, asked one model to act as a user, and another chat GPT we prompted it to act as a wizard.
Mhm.
And now these two instances of chat GPT are chatting to one another.
Okay, so did you use as a fine tuning or pre-training?
No, there is no fine tuning. This
Oh,
is
okay,
just
just
prompting.
using prompting. Okay.
Nothing is there. Just use OpenAI's API. One model is acting at this. So whatever this model sends, we send we send it to the other instance, and the other instance gets the, so essentially these ChatGPT is talking to one another but with different prompts.
Gotcha.
One is prompted to act as user, the other one is prompted to act as a wizard.
All right. Thank you.
There is no fine tuning there. But the model we are building after that, we have the data and everything. Of course, there is fine tuning there. This is the part where that you were referring to.
Yeah, we'll stop here. If you have, still have questions, talk to the speaker during the pizza time. So remember to sign in before you take the pizza. All right? Thank you very much. Okay.
Thank you all.